Okay.
We're starting. And we're going to finish up those examples that we started last time from 6.3/6.4. Okay, so we ended on an example that we ended up using logs to simplify. Which leads us to something that's called logarithmic differentiation. So this is a new differentiation technique. Perhaps. So here are the steps. And they're exactly the steps that we actually did last time to get that. When I asked you guys to differentiate, this was the square root of x times x plus 1 to the 3/2 over 2x squared plus 1 to the 7. And you could appreciate that doing that with the quotient rule and the chain rule and all that would have been very messy. But then we took a log of both sides. We called it y. Took the log of both sides, and we were able to find the derivative that way without too much sweat. But what we did wasn't just a standalone thing, it's an entire technique, and it's called logarithmic differentiation. Okay? So step one, given y equals f of x, this is all assuming the domain works out and all that stuff. Sometimes if your function is going to give you a negative value, what you can do is you can just factor that out, because derivatives have that property that you can factor negatives out. But it's something that you have to worry about. Make sure that you can actually log both sides, that this side will actually work inside a logarithm. Simplify both sides. So I gave you 9 log rules. You can use any one of them at any given time to simplify it. Step 3 is to differentiate both sides. Implicitly with respect to x. Of course, we're finding the derivative with respect to x. Okay, and at the end of the day, step 4, solve for y prime. So this technique is called logarithmic differentiation. When to use? Okay. So we saw that guy and we realized that doing that using our regular rules would be really messy. And so that's one reason why you might want to use something like logarithmic differentiation. F of x is very messy. And applying, usually it's going to be something like the quotient rule. And applying some sort of derivative rule would be very difficult to actually go through the mechanics of doing it. So when something is very messy, okay? And you realize that it has products and divisions and stuff, but you know that logarithms can break up products, they can break up divisions, they can turn powers into multiples, they can do all those sorts of things, and so it's very convenient to use it in the case of a messy function. Another case where you might want to use it is if there is a variable in the power. Let me do a silly example here to illustrate. Let's say you have y equals 2 to the x, and you want to find the derivative of that. Now we know a formula to find the derivative of that, okay? So we know there's a formula here that says, you know, to differentiate a to the x, it's a to the x ln a, sure. Okay, let's say you didn't remember that though. But you look at this function and you realize that the rules that I had before can't work, right? So you might think that, well, you shouldn't think, that the power rule would work. You bring this down, subtract 1 from the power, but that doesn't work here because it's not in the right form. The base is a constant, the power is a variable. The power rule applies when the base is the variable, the power is the constant. So when there's a variable in the power, it puts you in a position where your basic differentiation rules, they don't work. And so sometimes the formula is nice enough that if there's a variable in the power, we have a formula for it, but other times it's not. But let's say you forgot this formula this time around. You could actually solve this using log differentiation. So if you have y equals 2 to the x, you could have said, because there's a variable in the power, and you don't know a rule to deal with a variable in the power, you can remember, oh, logs turn powers into products, and I know the product rule. So what I can do is I can log both sides. That allows me to take that power down. And now I can differentiate both sides. This by the chain rule is y prime over y. This guy is going to be, this is just here is just a constant times x, so the derivative is just a constant. And so now I can say my y prime is actually going to be y times ln 2. But what was y? Y was 2 to the x. So you can get 2 to the x times ln 2. Right? Exactly what the formula would have given you. Now I don't expect you to actually differentiate this using log differentiation, but I'm just illustrating to you the power of this technique. It helps you to get a variable deal with variables in the power. An example that you might want to use this on is look at something like this. X raised to the x. Now that we don't have a rule for. And there are many cases where there are generic things like this, where you want to find the derivative of f of x, and it's raised to the power of another function. There's no general rule for that, right? So in situations like that, when you have variables in the power, log differentiation is very convenient, because that allows you to actually take that power down and actually use the product rule. Or sometimes you don't even need the product rule, right? So that's the power of this method. It helps you, for one, to simplify very messy functions that you want to take the derivative of, that you can use it to break down some of the operations. But also when there are variables in the powers and you don't have rules that cover that scenario. And yeah.
In that step, where did the x go when you differentiated from natural log y to y over y?
Oh, I differentiated, so it's just a constant. Derivative of a constant times x is just a constant, right?
Okay.
Derivative of 5x is just 5.
Yeah.
Derivative of 3x is just 3. So.
Okay, sorry.
Yeah. So that's just, this is a number, so it's like
Okay.
5x or 2x or whatever. When I differentiate, the x is.
Okay.
Okay. Right? So in situations like these, a log differentiation technique is the guide you want to turn to. If the base is a constant, you don't need it because we actually have formulas for that, but that won't always be the case. Here's a very simple example where the formulas that I gave you before, they won't work. And actually that was my next example. Let's actually do that guy. Let's do some examples here. So one example I wanted to do was a guy that we already did, so just let me say that this was done. B, I wanted to do this using log differentiation. Done. Next example. Right, and this was just an illustrative kind of example. I don't expect to use log differentiation or something like that. Let's differentiate x to the x. Now you would notice that we don't have a rule for this. We have a rule for a to the x and we have a rule for like x to the a, but we don't have a rule for x to the x. D. Let's differentiate x squared plus sine of x raised to the x. Okay, how would we do that? Walk me through the process.
Y equals x to the x.
Call that something. Set y equals x to the x. Clearly we want dy dx, which I would denote y prime from now on. Then,
Take the natural log of constant.
this means that ln of y is going to be equal to the ln of x to the x. And so we're using log differentiation. Now what?
Bring the exponent to the front.
This guy, by a log rule, says we can bring that exponent down to the front.
Now what? Differentiate.
Now we can differentiate. Derivative of this,
Y prime over
y prime over y by the chain rule. Derivative of this,
ln x plus x times 1 over x, which is 1.
right, or that's ln of x plus 1, right, by the product rule. This means that y prime is equal to y times this whole thing, ln of x plus 1, and so that means y prime is equal to x to the x times ln of x plus 1. And that's the derivative of that function. Questions on that? About 8? What do we do here?
Make y equals to x plus sine x
Now,
Take the natural log down to both sides.
what would I get here? Did I just take the ln of each one? Is that right?
Would
Yeah.
you take the natural log of the whole thing in parentheses?
Yes, that's wrong. Okay? Common mistake though, which is why I try to do it, to see who would agree with me. Yes, you cannot take the log of each individual sum because it is not true that if you take the log of something plus something, that is equal to log of this plus the log of that, right? By taking the log of each individual terms, it means that you believe this is true, which is not true, right? You take the log of both sides, which means you need to take the log of this entire thing, okay? One lesson to be careful about here. So it's ln of the entire thing.
You also can't distribute logs, right? Okay.
How would you deal with that? You make a face at it, let's read it. Yeah?
Like in the beginning, could you have taken the derivative of x squared and then the derivative of sine of x dx like separately? Like, can we do that? So you can put like,
Yeah, that's what I would do, actually. That was the right way to do. If you just jump and you're like, oh, there's a sine x to the x, log differentiation, you just like not think about it, just jump into this, you're going to end up with a problem here. Because you see this, you don't actually have a rule to simplify this, right? Because you have a sum of terms in here. We don't have any rules for log of a plus b. You should realize that. Okay, we don't have a simplification rule for that. So we'd kind of be stuck here. But one thing you can recognize is that I can just look at these things individually because there's a law of differentiation that says the derivative of a sum of terms is just the sum of each derivative individually. X squared, I already know how to differentiate x squared. It's not a big deal. I don't need this huge machinery of log differentiation to differentiate x squared. So I'd really just break them up into two parts. Okay. So I realize that this would just be the derivative of x squared plus the derivative of sine x to the x. Right? And I'm going to do log differentiation on this part. Well, on that part, it's just the power rule. Okay? And now you kind of, it's going to be kind of weird to write it all down here, but what I would do at this point is kind of go to the side. So at this point, to figure this one out, I go through the whole process. Set y equals sine x to the x. Log both sides. So this x comes down. Differentiate this y prime over y. What's the derivative of this?
Tangent.
This is where you come in. What's the derivative of this?
So ln sine x plus,
Right, you have to apply the product rule, right? You have x times something. These are two functions being multiplied. So you differentiate this, leave that, then you want to differentiate this, leave that. So that's x times what's the derivative of this?
1 over cosine. Isn't it tangent, isn't it cosine x over cotangent cosine x over sine x?
Yeah, it's cosine x over sine x, right? U prime over u. Right, don't forget the rules here. That you can write as cotangent if you want, which might just be easier to write it down. So this is x cotangent x. And so then you're going to multiply by the y. And so this will give you that your y prime is actually equal to the original function, which is sine x raised to the x times log of sine x plus x cotangent x. And so now we can come back to our original question. And you can say that this is equal to, we're going to differentiate x squared, which is 2x, plus, now you write this down. Yes?
Can you go
over where you got cosine over sine x?
I'm using the rule that the derivative of ln of anything is the derivative of the thing over the thing itself. So if I want to differentiate ln of sine x, this is going to be the derivative of sine x over sine x. Derivative of sine is cosine. Other questions? So the idea is you need to be careful when applying log differentiation. You can apply it across a sum. Okay, so if you have a sum of terms, you need to break it up and individually do log differentiation when it's appropriate. Okay? It might be combined with another function where you don't need it, you just use the power rule. So to go from this one to that one, I just used the power rule. Didn't need log differentiation. I'm going to show you an alternative here. And as far as I'm concerned, this is entirely a personal preference. Some people don't like the fact that they have to take one problem and break it into two separate problems. Okay? It's for psychological reasons, I don't know. So sometimes you can actually do a problem in one shot, and you can do it by kind of going around log differentiation, but you're still using the log and exponential rules. And the idea here is to somehow get a log in there without the need to actually split it up and separate it. And we're going to use a formula that we've used several times before, the fact that we know that anything we can write as e to the ln of that thing. So if the thing doesn't have a log, I could write it in a form where it now does have a log. Okay, so let's do an example with that. Let's go back over the simple one so you can kind of follow me here. Let's say you wanted to differentiate this, and you don't want to go separately. Okay, set y equals to this, differentiate both sides, blah, blah, blah. You could actually just rewrite this right away as e to the ln of x to the x. That's valid. And now what you do is you do the log rule in the power. And now what you do is you apply the rule. You know that the derivative of e to anything is just the derivative of the power times the original function. So what you're going to do is you're going to take the derivative of x ln x. This is just going to be x ln x derivative times the original function. This, again, you do the product rule. So that's going to be ln x plus 1. And this is that. But just remember that this e to the blah was just a rewrite of the original function, so I'm just going to copy back the original function. Right? And so you see, you've eliminated the need to go separately and define, oh, let y equals this and do that. You kind of eliminate that need right away. Okay. Did everyone understand what happened here? So you kind of do this trick where you realize that an ln could simplify this, but for one reason you prefer not to have to redefine a whole function and do implicit differentiation. You can actually rewrite it on the spot. Just do the rules using this guy, and you'll actually end up with the same answer. And you could actually do this without even thinking of it as a separate problem in the same way. We could actually just say, okay, that's equal to the derivative of e to the this is equal to the derivative of x squared plus the derivative of e to the ln of sine x dx. This here is 2x plus derivative of e to the x ln sine x is equal to 2x plus, and now you know you're going to differentiate the power and you're going to multiply by the original function. And so to derive the power now, you do the product rule and put it in here. That's going to be ln of sine x plus x times cotangent x. Okay. So you also have that option. But I do expect you to recognize that you have to use one of these options. So there are cases where you have to use log differentiation or kind of rewriting it using this rule when it's appropriate. So for something like x to the x, you don't have a rule for it. You'd have to do one of the two approaches. Okay? And it's personal preference which one you want to do. They both accomplish the same thing. They get something that might be messy to get an ln attached to it. Look at some integration. Tell me, what is the integral of ln x?
Isn't it something ln absolute value or I don't know.
The integral of ln x is ln absolute value?
Something I don't know. I remember learning something with an absolute value, but I might not be.
Okay. Yeah?
U ln of u minus u plus c.
Okay. That's correct. We don't know how to do this. It's just I just want to point that out. We know the derivative of ln x is 1 over x, but every now and then students get mixed up and they see this and they write 1 over x. I want to make sure that we don't do that. Okay. It's good to know what you don't know. Okay. All right. So we don't yet know how to do this, but we will. We'll do that actually very soon. To actually integrate something like ln x, we need a technique called integration by parts, and we're going to look at that. But for now, let's talk about integrals that result in ln x being in the answer. So consider this. The derivative of ln of absolute value of x. How would you define ln of the absolute value of x? How do you define absolute value of x? How's absolute value of x defined? You guys remember?
It's just,
X, x for x greater than or equal to 0, and then minus x for x less than 0.
Yes. Right. Of course, here we know that x cannot actually be 0, but we're going to apply that rule without the equal sign on it. But yes, in general, you'd be correct. So there are two things that this could possibly be. It's either the derivative of ln of x if your x is positive, or it's the derivative of ln of minus x if your x is negative. Right? Now, if your x is negative, taking the negative of it makes it positive, so it will work in the log. Now, what would that give you? Differentiate this? Well, we actually know how to do that. That's 1 over x. If x is greater than 0. What about this one? How do you differentiate ln of minus x?
doesn't exist.
How do you differentiate ln of anything?
U
U prime over u. Always have the rules in the front of your mind. How do you differentiate ln of minus x?
1 over x. it'd be negative 1 over
negative 1 over negative x, right? So it gives you 1 over x if x is less than 0. In either case, you get 1 over x. Right? Here's the takeaway. Therefore, by the fundamental theorem of calculus, we can say the following. The antiderivative of 1 over x dx is actually going to be the ln of absolute value of x plus c. The idea is here, if you look at the function 1 over x, it is possible for x to be negative, so I don't want to only care about the positive side. So sometimes whenever we want to deal with that situation, we see what happens to the absolute value when it breaks into a negative and positive. And so in this case, we realize that we can go back to the absolute value of x. So even if our x is negative, it will work. This formula does still hold. It will work for both positive and negative x's. It's a very important formula. So the derivative of ln x is 1 over x, but the integral of 1 over x is actually ln of absolute value of x. Yes, the absolute values are important. One thing I want you to note here in a weird way, this completes the power rule. Right? Remember when you were doing the power rule for integrals? There was literally one number that you couldn't touch in that rule. Right? When you had to do the integral of x to the n dx. Right? What was that? What was that?
Negative 1.
Well, no, it's x to the n plus 1 over n plus 1 plus c. But there was always a little comma here that says for n not equal to minus 1, right? That rule was all powerful for polynomials except for that one value. Well, for any power function of x, except for this one value. Why? Because you divide by 0 at that value. So, so the whole time we knew how to differentiate power functions of x, but we didn't have this value. But now we actually do, because now, if n equals minus 1, if you want to integrate x to the minus 1, you can just realize, oh, that's exactly the same as 1 over x. And so now we can actually get what that rule is. So that's a nice thing to know, that now that one little annoying gap that we had with the power rule, we've now filled that gap. Turns out the log function is the function necessary to fill that gap. So we have about a minute, so I'll write down some examples for this that you guys should try for next time. Yeah.
So is the derivative of natural log absolute value of x just 1 over absolute value of x?
No, it's 1 over x.
Okay.
Yeah.
Okay.
Because we did the piecewise, but they both gave us the same answer.
Oh, but it'll be different for the 1 over x because, yeah, okay.
Yeah. Because the 1 over x, the x here could be negative or positive.
Okay.
So without those absolute values, technically, if there's a negative, this x has a negative value, we'll be in trouble if we don't have the absolute values there.
Okay.
Do some examples. Try these on your own for Friday and we'll go over them. So we'll finish up these examples and then we'll start on the handout I gave you. So be sure to bring this to the next class with you. But in the meantime, try these guys out. said, by the time this course is done, you'll be able to find the integrals of some really nasty looking functions. But let's start off slow with these guys, something like this function. Try those for next time. So the homework isn't due. We haven't technically finished the section, but once we finish these examples, the homework will be due. So you can expect the homework for this, for both 6.3 and 6.4 will be due on Tuesday. So if you got through these and you feel pretty confident, just you can do the homework. Well, we'll actually look at those in class. So if there are no other questions, we can